4 days. That's how long the atmosphere over the central United States is about to come unglued. Tornadoes, giant hail, destructive winds from Texas to Minnesota starting Saturday, on repeat, and nobody's talking about why. Because the real story isn't the storms. The real story is 6,000 miles away, underneath the surface of the Pacific Ocean, where something is building that we haven't seen in nearly 30 years. Scientists are already calling it. The models are already diverging, and if they're right about what comes next, this weekend isn't a disaster, it's a dress rehearsal. Stay with me through this one, because by the end, you'll understand why the next 12 months on this planet might not look like anything we've planned for. Before we begin, if you genuinely enjoy what we do here at Project Nightwatch, hit like and subscribe so you do not miss a single update as the story unfolds. Drop a comment with where you're tuning in from, what time it is there, and tell me this. 4 days of tornadoes from Texas to Minnesota is what the preview looks like. So what does the main event look like when the most powerful El Nino in recorded history fully arrives on the hottest planet in human history? Let me know your thoughts in the comments. Now, let's get into it. Part 1. The 4-day convective lock-in. Right now, as you're watching this, the atmosphere over the central United States is doing something it shouldn't be doing in early April. A corridor stretching from West Texas to southern Minnesota is loading itself like a spring-driven mechanism that nobody asked to wind. 4 consecutive days of severe weather, not one event, not a single afternoon of bad storms, but 4 rotating cycles of destructive convection are about to unload across the American heartland starting this Saturday. We're talking damaging winds, large hail and tornadoes, not in some hypothetical model run, not in a speculative long-range forecast. This is happening within days, and the Storm Prediction Center is already escalating outlooks across multiple risk periods simultaneously, which, if you understand how conservative that agency tends to be, should tell you something important about the confidence level behind what's coming, and I need you to understand something before we go any further. What I'm about to walk you through over the course of this video is not a weather report. The 4-day outbreak is real, it's dangerous, and if you're anywhere in the threat zone you need to take it seriously. But the outbreak itself is not the story. The outbreak is the symptom. The story is what's producing it, why the atmosphere is behaving this way in the first place, and what it signals about the next 12 months on this planet. That's where we're going, but we start here, in the storm corridor, because this is where the signal is loudest. So let's talk about what's actually happening in the atmosphere right now. The jet stream across North America has locked itself into what meteorologists call a high-amplitude configuration. Picture the jet stream as a river of fast-moving air about 30,000 feet above the surface, normally flowing in gentle curves from west to east across the continent. Right now, that river isn't gently curving, it's bending in enormous, exaggerated waves, a trough plunging southward over the western United States and a ridge bulging northward over the southeast. That's the architecture. The trough acts as a storm generator, pulling energy and cold air southward. The ridge acts as a moisture pump, channeling warm, humid air from the Gulf of Mexico northward into the collision zone. And between those two features, in that corridor from Texas up through Oklahoma, Kansas, Missouri, Iowa, and into Minnesota, you get a conveyor belt of instability that fires storm after storm after storm. Now here's the part that makes this different from what you'd normally see in early April. In a typical severe weather setup, you get a discrete event. A single system moves through, triggers a day of storms, and then the pattern shifts. The front pushes east, the cold air settles in behind it, and the atmosphere resets. That's the normal cycle. That is not what's happening here. What we're looking at is a pattern where the front stalls, the jet stream holds its shape. The moisture feed from the Gulf keeps running, and the atmosphere essentially refires its convective cycle every 24 hours along roughly the same corridor. Day after day, same geography, same instability, same threat. Meteorologists have a way of describing this kind of setup, and the language they use tells you everything. They call it a stationary wave train producing sequential instability windows. Strip away the jargon, and what that means is this. The atmosphere has found a shape it likes, and it's holding that shape while pumping energy into the same zone repeatedly. The waves in the jet stream aren't moving, they're parked, and as long as they're parked, the storm factory stays open. This is a pattern you'd expect to see in late April or May, when the atmosphere has had weeks of warming to build the necessary energy gradients. Seeing it lock in this early, with this much persistence, is unusual. And if you're wondering whether that unusualness is random, whether this is just one of those years where things line up a little early, I want you to hold that question. Because the answer matters enormously, and it's not the one you might expect. The Gulf of Mexico moisture return right now is running at levels that are genuinely anomalous for the first half of April. The low-level jet, that's the river of warm, moist air flowing northward from the Gulf at around 3,000 to 5,000 feet, is stronger and more persistent than early April climatology would predict. It's acting less like a seasonal pulse and more like a continuous feed mechanism, the kind of sustained moisture pipeline you'd normally associate with a mature severe weather season. The storms aren't starving between cycles the way they usually would this early in the year. They're being refueled, and I want to give you a sense of the spatial scale here, because it matters for understanding why this isn't just a regional weather story. The threat zone stretches from roughly the Permian Basin of West Texas, north through the Red River Valley, across the Oklahoma and Kansas plains, through Missouri and Iowa, and up into southern Minnesota. That's over 1,000 miles of severe weather corridor operating simultaneously across multiple days. When the Storm Prediction Center issues enhanced or moderate risk outlooks over that kind of geography for multiple consecutive days, it means the system-level pattern is doing something significant, and this is the part that connects everything forward. This kind of persistent, repeating, locked-in severe weather pattern, where the jet stream parks itself in high amplitude mode, and the atmosphere behaves like a continuous energy release system, rather than a series of discrete events. This pattern has a signature. It resembles the atmospheric behavior you see during ENSO transitions. Specifically, it looks like what happens when the tropical Pacific is in the process of flipping states, when the ocean atmosphere coupling is reorganizing, and the mid-latitude jet stream starts responding to a signal that the official forecasts haven't fully acknowledged yet. That might sound like a stretch right now, a multi-day storm outbreak in the plains and something happening in the tropical Pacific. I get it. But by the end of this video, I think you'll see the connection differently, because what's happening beneath the surface of the Pacific Ocean right now is something we need to talk about. And it starts with a question that the atmosphere is already answering before the models have caught up. But first we need to talk about the energy, because the amount of fuel loaded into this system is not normal for April, and the numbers tell a story that the calendar doesn't want to admit. Part 2. Cape inflation and seasonal misalignment. There's a metric that atmospheric scientists use to measure how much explosive energy is stored in a column of air. It's called CAPE, convective available potential energy, and it's measured in joules per kilogram. Think of it as a fuel gauge for thunderstorms. The higher the CAPE, the more energy is available for storms to tap into when they fire. Low CAPE means weak, disorganized convection. High CAPE means the atmosphere is loaded and ready to detonate. For early April across the central United States, climatological CAPE values typically sit somewhere between 500 and maybe 1,200 joules per kilogram on an active day. That's enough to produce thunderstorms, maybe some hail, occasional wind damage, standard early season activity. What we're seeing in the current atmospheric profiles and what models are projecting for this weekend's outbreak window is CAPE values between 2,000 and 3,000 joules per kilogram. Some model runs are pushing even higher in localized corridors. Let me put that in perspective. 2,000 to 3,000 joules per kilogram is late May energy. That's the kind of instability you'd expect during the climatological peak of tornado season, not the opening weeks of April. The atmosphere is, for lack of a better phrase, overcharged for the calendar date. It's carrying energy reserves that belong to a season 6 weeks in the future, and it's releasing them now. And this isn't just about one number on one chart. The entire vertical profile of the atmosphere is misaligned with where it should be seasonally. The moisture depth in the low levels, the thickness of that warm, humid layer being transported northward from the Gulf, matches what you'd typically see in late May or early June Gulf profiles. The dew point values at the surface and just above are running several degrees above early April normals. That matters because moisture is fuel. Every degree of additional dew point temperature represents more water vapor in the air, more latent heat available for release when that moisture condenses inside a thunderstorm updraft, and more total energy the storm can convert into wind, hail, and rotation. Now layer the wind shear on top of that. Wind shear, the change in wind speed and direction with altitude, is what organizes thunderstorms into supercells. the rotating monsters that produce the most destructive tornadoes. In early April, strong wind shear is common because the jet stream is still active, but it usually exists in an environment where instability is relatively modest. You get shear without fuel. The storms might rotate briefly, but they don't have the energy to sustain intense long-track tornadoes. What makes this setup so unusual is that both parameters, instability and shear, are simultaneously elevated and overlapping across the same geography. The wind shear corridor extends unusually far north, pushing well into the upper Midwest into areas where tornado risk in early April is climatologically rare. And that brings us to something that should make you pay attention, even if you're not a weather enthusiast. The models are showing legitimate tornado potential in southern Minnesota during this outbreak window. Minnesota in April. Now, Minnesota does get tornadoes, it's not unheard of, but the climatological peak for Minnesota tornadoes is June and July, not the first half of April. Seeing a credible severe weather setup with tornado risk extending that far north this early in the season is a displacement anomaly. The tornado risk corridor has shifted northward, relative to where the calendar says it should be. This connects to something I want you to think about as a concept, because it's going to matter for the rest of this video. What we're witnessing isn't just an early start to severe weather season, it's what I'd call seasonal compression. The atmospheric parameters that would normally develop gradually over weeks and months are stacking up simultaneously in a compressed window. Instead of instability building slowly through April, peaking in May, and combining with shear in a progressive sequence, everything is arriving at once. The energy is here, the shear is here, the moisture is here, and they're all peaking together in early April across an unusually large geographic envelope. The Gulf of Mexico is a major reason for this. Sea surface temperatures in the Gulf are running well above average right now, and that matters directly for severe weather because warmer ocean surfaces produce more evaporation, more water vapor, and more efficient moisture flux into the atmosphere. When the low-level jet taps into a Gulf that's running anomalously warm, the moisture transport isn't just sustained, it's enhanced. The atmosphere gets more fuel per unit of wind, which means the instability ramps up faster and higher than it would over a cooler ocean surface. And here's something that researchers have been tracking in recent severe weather seasons. In years where ocean temperatures are elevated, not just in the Gulf but globally, storms have been reaching destructive thresholds at lower Cape values than historical norms would predict. The atmosphere seems to be becoming more efficient at converting available energy into severe weather. A storm that might have needed 3,000 joules per kilogram to produce a significant tornado, 20 years ago might now do it at 2,000. The thresholds are shifting, the system is not operating the same way it used to. So when I tell you that Cape values of 2,000 to 3,000 joules per kilogram are forecast for this weekend, understand that the effective output of that energy may be even greater than those numbers suggest on their own. The atmosphere isn't just carrying more fuel, it's burning that fuel more efficiently. And all of this raises a question that goes beyond this weekend, beyond this specific outbreak. If the atmosphere is running this hot this early, with this much synchronized energy, what's driving it? Is this just a statistical blip? A random alignment of favourable conditions that happen to arrive a few weeks ahead of schedule? Or is there something larger reorganising the atmospheric pattern from the outside? Something that would explain not just the intensity of this outbreak, but the persistence of the jet stream configuration, the anomalous moisture transport, and the seasonal displacement of the entire severe weather corridor? Because there is something, and it's not hiding. You just have to know where to look, and it isn't in the atmosphere at all. It's in the structure of the wave pattern that's producing all of this, a pattern that has a fingerprint if you know how to read it. Part 3. The hidden driver. Pattern amplification, not randomness. Let me take you up to about 30,000 feet, not inside a storm but above the entire weather pattern, looking down at the northern hemisphere from a satellite's perspective. From up here, you can see the jet stream not as a local feature over the United States, but as a planetary-scale wave system that wraps around the entire globe. These waves have a name, Rossby waves, named after the Swedish-American meteorologist Carl Gustaf Rossby, who first described them in the 1930s. They're the fundamental organising structures of mid-latitude weather, and right now, they're doing something that should concern you. Rossby waves are always present in the jet stream. They're the reason weather patterns move and change, the troughs and ridges that bring alternating periods of storms and calm. In a normal jet stream configuration, These waves have moderate amplitude, they curve but not dramatically, and they move. They propagate eastward, which means weather systems come and go. A storm hits, passes through, and the pattern evolves. What's happening right now over North America is that the Rossby wave pattern has amplified, the waves have gotten taller and deeper, and it has slowed down. The trough over the western United States and the ridge over the southeast aren't just present, they're locked in place with exaggerated vertical extent. The jet stream isn't gently curving, it's making enormous north-south excursions, pulling Arctic air deep into the west while pumping subtropical moisture far into the upper Midwest. And because the pattern is slow-moving, these extremes persist. Day after day, the same corridor gets hammered. This is what drives the multi-day outbreak we just discussed. It's not that storms are forming randomly across the plains, it's that the Rossby wave architecture has created a semi-permanent storm factory, and it keeps running because the wave pattern refuses to move. Now, why would Rossby waves amplify and stall like this? There are several contributing factors, but one of the most significant is the thermal gradient structure of the ocean surface. When you heat the ocean unevenly, warmer in some regions, cooler in others, the atmosphere responds by adjusting its circulation patterns. Stronger temperature contrasts between ocean regions generate stronger pressure gradients in the atmosphere, which in turn amplify the jet stream waves. And right now, the temperature contrasts across the Pacific Ocean are shifting in a way that has a very specific signature. The Gulf of Mexico, which we've already discussed as the moisture source for this outbreak, is acting as an amplifier, but the Gulf isn't operating in isolation. It's part of a larger oceanic feedback loop where warm ocean surfaces enhance evaporation, increase atmospheric moisture content, and release latent heat when that moisture condenses inside storms. That latent heat release feeds back into the jet stream, reinforcing the ridge trough pattern and making it more persistent. The atmosphere and the ocean are talking to each other, and right now they're having a very loud conversation. This is where I need you to shift your frame of reference. Because everything I've described so far, the locked-in jet stream, the persistent storm corridor, the amplified Rossby waves, the Gulf moisture feedback, all of this is the atmosphere responding to something. The atmosphere doesn't generate its own energy. It receives energy from the ocean surface, from solar heating, from the redistribution of heat across the planet. When the atmosphere starts behaving in amplified, persistent, unusual ways, the first question a scientist asks is, what changed in the forcing? And when you look at the forcing, when you look at what the tropical Pacific Ocean is doing right now, you find something that reframes everything I've told you so far. The ENSO system, the El Niño Southern Oscillation, the single most powerful natural climate driver on Earth, is in the process of flipping states. We've been in a La Niña pattern, with cooler than average waters in the central and eastern equatorial Pacific. But that pattern is collapsing, and the system is accelerating toward neutral and potentially beyond, toward El Niño. The Climate Prediction Center currently gives roughly a 62% probability of El Niño developing by later this year, and some model runs suggest it could happen faster and harder than the official outlooks imply. Now here's the important tension. ENSO is not officially in an El Niño phase yet. We're in a transitional state, so why is the atmosphere over the United States already behaving like it's responding to El Niño-like forcing? Why are the jet stream patterns, the moisture transport anomalies, the seasonal displacement of severe weather, why do these features resemble what you'd expect during an active ENSO event? That's the question I want you to carry into the next section of this video, because the answer isn't in the atmosphere, it isn't in the jet stream or the CAPE values or the storm reports. The answer is underneath the surface of the Pacific Ocean, where something has been building for months that most people haven't heard about, and most forecasts haven't fully captured. The atmosphere might be telling us something that the official ENSO forecast hasn't admitted yet. And if it's right, what's coming this weekend is not an outlier, it's a preview. Part 4. ENSO Flip Acceleration. The equatorial Pacific Ocean is the largest single driver of year-to-year climate variability on Earth. When it warms, El Niño, the consequences ripple across every continent. When it cools, La Niña, a different set of consequences follows. And when it transitions between those states, the atmosphere goes through a period of reorganization that can produce exactly the kind of amplified, unusual weather patterns we've been discussing. Right now, the ENSO system is transitioning out of La Niña faster than most seasonal models anticipated. The Oceanic Nino Index, the ONI, which is the primary metric for tracking ENSO state, has been trending upward toward neutral, and the rate of change is outpacing the typical climatological curve. In a standard La Niña decay, you'd expect a gradual warming through spring, reaching neutral by midsummer, with El Niño development, if it happens, beginning in late summer or fall. What the data is showing instead is an accelerated timeline. The cooling signature is weakening faster than expected, and the ocean-atmosphere coupling indicators are shifting in ways that suggest the system isn't easing gently into neutral, it's being pushed. The Climate Prediction Center's current probabilistic outlook assigns approximately 62% odds of El Niño formation by the second half of 2026. That number sounds moderate, and in some ways it is. CPC is deliberately conservative in its outlooks, especially during the spring predictability barrier, which is a well-known period between March and May when ENSO forecast skill drops significantly. The atmosphere and ocean decouple slightly during this window, making it harder for models to project what happens next. It's a forecasting dead zone, and CPC accounts for that by keeping probabilities measured. But here's what the raw probability number doesn't capture: the rate of transition and the nature of the early signals. ENSO transitions are often non-linear. They don't follow smooth curves from one state to another. They can accelerate abruptly, what some researchers informally call a snap transition, where the system tips from weakly cool to rapidly warming in a matter of weeks once certain thresholds are crossed. The atmospheric response typically lags the oceanic signal by several weeks to a couple of months, which means that by the time the atmosphere fully adjusts to a new ENSO state, the ocean has often already moved further than the atmosphere is reflecting. And this is where I want to bring you back to the storms. Because if the ENSO system is accelerating through its transition faster than models predict, and if the atmospheric response lags the ocean signal, then the unusual weather patterns we're seeing over the United States right now, the locked-in jet stream, the amplified Rossby waves, the anomalous moisture transport, the seasonal compression of severe weather, could be the atmosphere's early-stage response to an ENSO transition that the official forecasts haven't fully captured yet. The atmosphere might be the leading indicator here, not the lagging one. It might be telling us where the Pacific is going before the ONI numbers confirm it. Not all neutral states become strong El Niño events, that's important to say. The system could stall in neutral, or produce a weak, short-lived El Niño that doesn't generate the kind of global-scale consequences we'll discuss later. Scientific caution is warranted, but the speed of the current transition, combined with the atmospheric anomalies already appearing over North America, suggests that something more significant than a routine seasonal shift is underway. And the strongest evidence for that isn't at the surface of the Pacific at all, it's below the surface. In a layer of the ocean that most people never think about, something has been accumulating for months, a reservoir of energy that, if released, could fuel one of the most powerful El Niño events in recorded history. Part 5. Subsurface Kelvin wave loading. Imagine the Pacific Ocean not as a flat surface, but as a three-dimensional body of water with layers. At the top, you have the warm layer, heated by the sun, mixed by the wind, and directly interacting with the atmosphere above. Below that, separated by a boundary called the thermocline, sits much colder, denser water. The thermocline is like a floor beneath the warm pool, and its depth varies across the Pacific. In the Western Pacific, it sits relatively deep. The warm layer is thick. In the Eastern Pacific, near the South American coast, it sits shallow. The warm layer is thin. This layered structure is the engine room of ENSO. During La Niña, the thermocline tilts, deeper in the west, shallower in the east, and trade winds push warm water westward, piling it up near Indonesia and Australia. The Eastern Pacific stays cool. That's the La Niña configuration, and it's the state the Pacific has been in recently. But here's what matters for our story. During the decay phase of La Niña, heat begins to accumulate beneath the surface in the western and central Pacific. Not at the surface, where satellites can easily see it, but in the subsurface layers, the upper few hundred meters of ocean. This heat doesn't show up on sea surface temperature maps. It's invisible to the casual observer. But it's there, stored like energy in a battery waiting for a trigger. That trigger comes in the form of Kelvin waves. A Kelvin wave is a pulse of warm water that propagates eastward along the equator, driven by changes in wind patterns over the western Pacific. When the trade winds weaken or reverse, which can happen during westerly wind bursts associated with the Madden-Julian Oscillation or other tropical disturbances, they launch these warm water pulses eastward. The Kelvin wave travels beneath the surface, pushing the thermocline downward as it goes, and when it reaches the eastern Pacific it causes the thermocline to deepen there. Suddenly the cold water that was close to the surface is pushed down, the warm layer thickens, and sea surface temperatures begin to rise. That's the birth of an El Nino signal at the surface. What oceanographers are observing right now in the equatorial Pacific subsurface is significant. There are indications of anomalous warm water accumulation beneath the surface in the central Pacific, the kind of subsurface loading that precedes major El Nino development. The thermocline appears to be in the early stages of flattening, which means the heat stored in the western Pacific is beginning to redistribute eastward. Kelvin wave activity has been detected, and the subsurface temperature anomalies are tracking in a way that resembles the precursor phases of previous major El Nino events. And I want to draw a comparison here that puts this in historical context. In 1996 and early 1997, before the Super El Nino of 97-98, one of the strongest ever recorded, the subsurface Pacific showed a similar pattern of heat accumulation and Kelvin wave propagation. At the surface, things looked relatively normal for months. The ONI was near neutral, the atmosphere hadn't fully responded, but underneath, the ocean was loading itself with an extraordinary amount of thermal energy, and when that energy finally surfaced, the result was explosive. Sea surface temperatures in the eastern Pacific spiked by more than 4 degrees Celsius above normal. Global weather patterns were thrown into chaos. Floods in California, droughts in Indonesia, coral bleaching events across the tropics. The 97-98 El Nino caused an estimated $35 billion in damage worldwide. Now, I am not telling you that we are guaranteed to repeat 1997-98. The Pacific doesn't replay old scripts exactly. Every ENSO cycle has its own character, its own timing, its own feedbacks. But the subsurface signature right now, the heat accumulation, the Kelvin wave activity, the thermocline behavior, is consistent with a system that is storing significant energy for potential release. And if that energy surfaces rapidly, the El Nino that develops could be substantially stronger than what the official probability forecasts currently suggest. Think of the ocean as a battery that's been charging for months during La Niña. The energy is stored beneath the surface, out of sight, building potential. The Kelvin waves are the discharge mechanism. When they propagate east and the thermocline flattens, the battery dumps its energy into the surface layer and, from there, into the atmosphere. The atmospheric response, the jet stream reorganization, the amplified weather patterns, the global teleconnections, follows. And this is the critical link back to what's happening over the United States right now. The multi-day severe weather outbreak, the locked-in jet stream, the anomalous Cape values, the seasonal compression, all of it sits downstream of an atmosphere that appears to be responding to Pacific forcing that the surface data hasn't fully revealed yet. The subsurface ocean is sending a signal. The atmosphere is receiving it. And the storms rolling across the plains this weekend may be among the first visible expressions of a Pacific energy transfer that has barely begun. The surface SST data lags the subsurface signal. That's a fundamental feature of ENSO dynamics. By the time you see it at the surface, the subsurface has already moved. The subsurface gives you advance warning, if you're paying attention. And right now, the subsurface is saying something that the surface hasn't confirmed yet. The question is whether the models are listening, and that, as it turns out, is a problem all by itself. Part 6. The Model Divergence Problem. Here's something that most weather and climate videos won't tell you, because it's messy, and it doesn't make for a clean narrative. The forecasting models don't agree on what happens next. Not in the way that models normally disagree, slightly different projections clustered around a common central estimate, but in a way that represents a genuine material divergence about outcomes that differ enormously in their consequences. Understanding that disagreement, what it means, why it exists, and what it implies for the range of possible futures we're looking at, is more important than any single forecast number. The number is less informative than the spread, and right now, the spread is telling you something. The Climate Prediction Center, CPC, is the official US government source for ENSO outlooks. Their current forecast puts El Nino probability at roughly 62% for the latter part of 2026. That's their probabilistic assessment, weighted across a suite of dynamical and statistical models, adjusted for the spring predictability barrier, and delivered with the institutional caution that characterizes government forecasting agencies operating under the constraint that their public communications must be defensible, reproducible, and calibrated to historical forecast performance. It's a measured number, a responsible number. A number that reflects the genuine uncertainty in the current observational picture and the known limitations of the forecasting tools being applied to it. But it is also a number that represents a central tendency, and central tendencies, in a system whose consequences scale non-linearly with intensity, can obscure the most important information which lives in the tails. The European Centre for Medium-Range Weather Forecasts, ECMWF, which runs one of the most sophisticated coupled ocean-atmosphere models in the world, and whose operational forecasts are widely regarded as the global benchmark for medium-range prediction, is showing a somewhat stronger El Nino signal in its ensemble mean. Their model runs, on average, project more rapid warming in the Nino 3.4 region, the area of the central and eastern equatorial Pacific, whose sea surface temperature anomalies define the ENSO index and tend to cluster at higher SST anomaly values compared to the CPC multi-model mean. The ECMWF isn't predicting a super El Nino per se, and it would be a mischaracterization to present its output that way. But its central estimate runs warmer and faster than what CPC's more conservative, multi-model consensus approach suggests, and the difference between those two institutional assessments is itself informative. When the most sophisticated coupled modelling system in the world is consistently running warmer than the conservative multi-model mean, that asymmetry deserves attention. And then there's the ensemble spread, the range of outcomes across all the individual model members within each forecasting system, the full distribution of possible futures that the models are collectively generating. This is where the picture becomes genuinely concerning, because the spread is wide, very wide, wider than you'd want it to be at this stage of a developing ENSO event. On the low end, some model members show ENSO peaking as a moderate El Nino, with Nino 3.4 anomalies around plus 1.5 degrees Celsius above normal, a notable event, certainly disruptive in some regions, but within the range of what the global agricultural and economic system has absorbed before without catastrophic failure. On the high end, some members project anomalies exceeding plus 3 degrees Celsius, which would place the event in historically extreme territory, rivaling or exceeding 1997 to 1998 and 2015 to 2016, the two strongest El Nino events in the modern instrumental record. That is an enormous range. It is not a rounding error or a minor calibration uncertainty between models with slightly different parameterization schemes. The difference between a plus 1.5 and a plus 3 degree El Nino is not a matter of degree in any casual sense. It is the difference between a notable climate event and what some researchers have not shied away from calling a civilization-scale disruption. It is the difference between some regional crop stress affecting a handful of producing countries and synchronized multi-breadbasket failure that overwhelms the global food trading system's capacity to redistribute supply. It is the difference between elevated commodity prices that stress household budgets and potential food crises that destabilize governments in import-dependent nations with limited fiscal buffers. And right now, with the models in their current state of disagreement, the forecasting community cannot confidently distinguish between those outcomes. That is not a communication failure. It is an honest reflection of the state of scientific knowledge at this moment in the ENSO development cycle. This is partly explained by the spring predictability barrier, which is the most important concept in seasonal climate forecasting that almost nobody outside the field has heard of. Every year, between roughly March and May, ENSO forecast skill drops, measurably, consistently, across every forecasting system that has ever been evaluated against historical outcomes. The reason is that the ocean atmosphere coupling in the tropical Pacific weakens during spring. The signals that models rely on to project future ENSO development, the feedback between sea surface temperature anomalies and atmospheric circulation, the Walker circulation response, the westerly wind bursts that can lock in positive feedbacks and accelerate El Nino development, become noisy and less coherent during this seasonal window. It's a known limitation, extensively documented in the scientific literature, and it affects every forecasting centre on the planet without exception. Forecasts made in April for conditions in October or November carry inherently larger uncertainty than forecasts made in July for the same target months, not because the models are worse in April, but because the system itself is less predictable during this window. We are in that uncertainty window right now, and the model spread is reflecting that reality faithfully. But there's a deeper issue beyond the seasonal forecast challenge, one that persists even after the spring predictability barrier is cleared. In ENSO transitions, particularly rapid ones where the system moves from La Niña to a developing El Niño over a compressed time frame, models have historically struggled to capture the full magnitude of the event until it is already well underway. The 1997 to 1998 event is the canonical example, and it's worth understanding in some detail because the parallels to the current setup are uncomfortable. Models in early 1997 were broadly forecasting neutral to weak El Niño conditions for the remainder of the year. There was awareness of some oceanic warming in the subsurface, the kind of subsurface heat loading that is also present in the current Pacific, but the models did not translate that subsurface signal into strong surface warming projections. By summer of 1997, the Pacific had already entered one of the fastest developing and ultimately strongest El Niño events in the observational record. The models didn't see it coming at the magnitude it arrived, and the primary reason was that they underweighted the subsurface signal. They were calibrated more heavily on surface data and atmospheric indicators, and the subsurface heat loading, the Kelvin wave dynamics propagating eastward along the thermocline shoaling in the eastern Pacific that set the stage for rapid SST warming, was not given sufficient weight in the forecast equations. By the time the models caught up to what the ocean was already doing, the event had already locked in. Models have improved significantly since the late 1990s. This is worth acknowledging clearly. Ocean data assimilation is better. The Argo Float network, which didn't exist in 1997, now provides continuous subsurface temperature and salinity observations across the global ocean that are assimilated into model initial conditions in near real time. Coupled models resolve the ocean atmosphere interaction with greater fidelity. Ensemble approaches that sample forecast uncertainty more systematically have replaced deterministic single model runs at most operational centres. The 1997 to 1998 event would almost certainly be better anticipated today than it was at the time. But the fundamental challenge remains. In years when the system is transitioning rapidly and non-linearly, when positive feedbacks are accelerating development faster than the smooth climatological evolution that models are implicitly calibrated to expect, models that assume relatively gradual ENSO evolution tend to underestimate the speed and ultimate intensity of the transition. They catch up eventually, but by the time they fully resolve the magnitude of what's happening, the event is already well underway and the preparation window is narrowed. This brings us to what I think is the most important framing for understanding what we're currently watching, the scenario bifurcation that the model ensemble is showing right now. The distribution of model outcomes isn't uniform, it has structure. There are two broad clusters. One cluster shows a strong El Niño developing by late 2026, with Nino 3.4 anomalies in the plus 1.5 to plus 2 degree range. Significant, impactful, capable of producing the kinds of agricultural disruptions and commodity market stresses that we've seen during previous strong events, but within the range that the global system has, at some cost, absorbed before. The other cluster shows something qualitatively different, a super El Niño with anomalies pushing toward or beyond plus 3 degrees, developing faster than the ensemble mean suggests and potentially peaking earlier than seasonal models expect, carrying the kind of atmospheric forcing that reorganizes planetary circulation patterns rather than merely nudging them. The difference between those two scenarios, in terms of global consequences, is not linear. It is not the case that a super El Niño is simply twice as disruptive as a strong El Niño. The relationship between ENSO intensity and its downstream effects on jet stream configuration, on monsoon behaviour, on agricultural production across multiple breadbasket regions simultaneously, on commodity markets, on the frequency and intensity of extreme events, is deeply nonlinear. A moderately strong El Niño shifts patterns. A super El Niño can break them, pushing regional climate systems past thresholds that produce impacts qualitatively different from what scaled linear extrapolation would suggest. The 1997 to 1998 event didn't just produce more of what previous strong events had produced. It produced failures in systems that had functioned through previous events, because the forcing was strong enough to overwhelm mechanisms that had previously provided partial buffering. On a planet that's already running at record-high baseline temperatures, that same ENSO forcing, superimposed on a warmer ocean, a more moisture-laden atmosphere, more energetically primed storm environments, scales into consequences that our historical experience may not fully capture. The analogy breaks down precisely at the point where we need it most, because we have never run this experiment before. The models are telling us, clearly and consistently, that El Nino is coming. On the direction of change, there is genuine convergence. La Nina is ending, the Pacific is warming, the transition is underway. What they don't agree on, what the wide ensemble spread directly encodes, is the magnitude. And in a system that is accelerating through its transition phase, with subsurface energy loading that some models may not fully resolve, and with a baseline thermal state that has no direct historical analogue, the risk is skewed toward the high side of that distribution. Not guaranteed, not certain. But the probability distribution has a fat right tail, a warm tail, and that tail represents outcomes that the global agricultural system, the global supply chain infrastructure, and the global financial system are not prepared for in any serious operational sense. So where does this leave us? We have an atmosphere over the central United States already behaving anomalously, a jet stream locked into an amplified Rossby wave configuration, severe weather parameters compressed into a narrow seasonal corridor, an outbreak unfolding across 4 consecutive days with the kind of persistence that reflects planetary scale forcing rather than local weather noise. We have a Pacific Ocean that is transitioning out of La Nina faster than its recent historical pace, with subsurface heat loading that resembles the precursor phases of major historical El Nino events more than it resembles the precursor phases of moderate ones. And we have a forecasting community that broadly agrees on the trajectory of what's coming, but is genuinely, materially and honestly uncertain about the magnitude. Uncertain enough that the two ends of the model distribution describe worlds that are not meaningfully comparable in terms of their human consequences. The storms this weekend are real and immediate. The damage they leave behind is concrete and local. But they exist within a context that stretches months into the future and thousands of miles across the Pacific. And that context is about to collide with something that changes the entire calculus of what El Nino means in the modern era. A planet that is already hotter than it has been since the beginning of systematic climate observation, and warming still. That collision is what the models are trying to capture, and at the moment failing to agree on. The disagreement is not a reason for dismissal. It is the most important signal in the data. Part 7. ENSO isn't the same system anymore. I need to tell you something that fundamentally reframes everything we've discussed so far. It's not complicated, but it has consequences that most coverage of El Nino fails to adequately capture, and once you understand it, you cannot look at this weekend's outbreak the same way again. El Nino is a natural oscillation. It has been happening for thousands of years, a periodic warming of the eastern equatorial Pacific that shifts atmospheric circulation patterns across the entire globe. In isolation, it is a well-understood system. Scientists know the teleconnections. They know which regions get wetter, which get drier, where storm tracks shift, how agricultural zones respond, how commodity markets react. There are decades of observational data and a mature body of scientific literature built around this single recurring phenomenon. In many ways, El Nino is the most studied climate pattern on Earth. But here is what has changed, and this is the part that most coverage glosses over, skips entirely, or buries in the final paragraph where nobody reads it. El Nino is no longer arriving on a normal planet. The global ocean is right now running at or near record high sea surface temperatures. Not record for the month, not record for the season, record. Full stop. The baseline, the average temperature of the ocean surface from which El Nino anomalies are measured, has shifted upward significantly over the past several decades, and that shift has accelerated sharply in recent years in ways that have surprised even the researchers tracking it most closely. 2023 was the warmest year in the instrumental record. Then 2024 arrived and exceeded it. The ocean heat content integrated across the top 2,000 meters of the global ocean is at record levels. The planet is carrying more thermal energy in its climate system than at any point in modern human history. That is not a forecast. That is the current measured state of the ocean right now, today, as the storms this weekend are loading themselves with Gulf moisture and preparing to roll across the plains. And this matters for El Nino in a way that most public discussion fundamentally underestimates. When the Climate Prediction Center describes an incoming El Nino as a +2 degrees Celsius anomaly in the Nino 3.4 region, they are talking about a departure from the current average, a deviation from baseline. But here is the critical distinction that gets lost every single time this conversation happens in public. The current average is itself anomalously warm. The baseline has moved, so the absolute temperature, the actual number on the thermometer in the eastern equatorial Pacific, during a strong El Nino on today's planet is higher than it would have been during an equivalent anomaly in 1997 or 1982, or any previous event in the observational record. The anomaly might be the same magnitude. The absolute temperature is in territory we have never measured before. This distinction between anomaly and absolute temperature is not a technical footnote. It is the entire story, and it is one that gets lost almost universally in public communication about ENSO. When an official forecast says strong El Nino, what they mean is a certain magnitude of departure from the baseline. But the atmosphere does not care about departures from baseline. The atmosphere does not read the anomaly charts. The atmosphere responds to absolute energy, and absolute energy scales with absolute temperature, not with how far that temperature sits above an average. A 2-degree El Nino anomaly on a planet that is already half a degree warmer than it was 30 years ago produces atmospheric energy levels that are not just anomalous, they are unprecedented. There is no historical analogue. There is no prior event we can point to and say, last time this happened, here is exactly what followed. Let me bring this directly back to the storms we started with, because the connection is not abstract. The Cape values being forecast for this weekend's outbreak, 2,000 to 3,000 joules per kilogram over the central United States in early April, are a product of the absolute temperature and moisture content of the atmosphere, not the anomaly values. The Gulf of Mexico is not contributing record moisture to this storm system because the El Nino anomaly is enormous. El Nino has not even officially arrived yet. The Gulf is contributing record moisture because its absolute sea surface temperature is at record levels, because the global ocean baseline has shifted beneath it, and because the atmosphere sitting on top of that warmer water holds more water vapor, more latent energy, and more convective potential than it would have at any previous point in the observational record. The storms this weekend are not being fueled by an anomaly. They are being fueled by a new normal that is itself abnormal. This is what researchers mean when they use the phrase same signal, different outcome. An El Nino of the same anomaly magnitude as the 1997-98 super event, one of the most destructive climate events of the 20th century, arriving on today's warmer planet would produce fundamentally different and almost certainly more severe atmospheric consequences. More moisture available at every level of the atmosphere, higher absolute temperatures feeding storm updrafts, greater latent heat release inside convective systems, stronger pressure gradients driving surface winds, more intense extremes across every category we measure. The signal is familiar. The outcome has no precedent. The physics behind this is not speculative. The Clausius-Clapeyron relationship is one of the most well-established equations in atmospheric science. It tells us that the atmosphere's capacity to hold water vapor increases by approximately 7% for every degree Celsius of warming. 7% sounds modest until you understand what it means in practice. A warmer planet does not produce the same storms at a slightly higher temperature. It produces storms with fundamentally more fuel loaded into every cubic meter of air they consume. Precipitation rates scale upward. Wind speeds inside convective systems increase. Hail grows larger because updrafts carry more energy to sustain larger ice particles at altitude. Tornado environments become more energized because the instability and moisture that feed rotating supercells are both elevated simultaneously. And critically, this is not a proportional or linear increase. The relationship between absolute temperature, moisture content, and severe weather potential is non-linear. The energy available for severe convection scales, with both parameters moving in the same direction at the same time, and the result is an atmosphere that does not just produce slightly worse storms, it produces a categorically different storm environment. The consequences extend well beyond severe weather, and this is where the weekend's outbreak connects to something much larger than tornado warnings. Coral reefs across the tropical oceans are already under unprecedented thermal stress from the elevated baseline alone, before El Nino adds its additional warming on top. The thermal margin, the buffer zone between current ocean temperatures and the bleaching threshold beyond which coral colonies die, has been shrinking for decades. It is now, in many reef systems, dangerously thin. A strong El Nino arriving on today's baseline does not push ocean temperatures to levels that stress coral reefs. It pushes them to levels that could trigger mass bleaching events, exceeding anything previously observed in the scientific record. The ocean ecosystem storyline runs parallel to the atmospheric one, driven by the same fundamental forcing: more energy in the system than the planet has carried at any point in the era of modern measurement. The scientific community continues to debate the precise degree of amplification. The relationships involved are complex, the feedbacks are difficult to model with precision, and honest researchers will tell you that the uncertainty at the high end is real and significant. But on one point there is no serious scientific dispute. The direction of the effect is settled. Warmer baseline plus El Nino equals more extreme outcomes. The magnitude of that amplification remains uncertain, the sign does not. Every credible analysis of this question points in the same direction, and the only genuine debate is how far in that direction we're about to travel. And the storms rolling across the central United States this weekend, the 4-day outbreak, the anomalous Cape values running 6 weeks ahead of the seasonal calendar, the northward displaced tornado risk reaching into Minnesota in early April, the seasonal compression of every severe weather parameter simultaneously. This may be what the early stages of that amplified response look like in real time. Not a random alignment of favourable conditions, not a statistical blip in a noisy record. But the atmosphere beginning to express in the most direct and visible language it has what happens when a powerful natural oscillation that has shaped global weather for thousands of years fires into a climate system that is already carrying more energy than it ever has. If that reading is correct, and the next several months of data will tell us, then what is coming this weekend is not the story, it is the prologue. The atmosphere over the central United States is not showing us the worst of what this system can produce. It is showing us the opening act of a performance that has not yet found its full voice. The jet stream is locked, the Pacific is loading, the baseline has already shifted. What comes next is not a weather event, it is a reckoning. Part 8. Jet stream rewiring mechanism. The jet stream is a creature of temperature gradients. It exists because the equator is warm and the poles are cold, and the atmosphere needs a mechanism to transport heat from one to the other. That mechanism is the jet stream, a river of fast-moving air at roughly 30,000 feet that circles the entire planet, carrying energy from the tropics toward the poles in a continuous, restless cycle. The greater the temperature contrast between equator and pole, the stronger and more focused that river becomes. The more uneven that contrast, warm in some places, sharply cold in others, with abrupt boundaries between them, the more the jet stream amplifies into those extreme, exaggerated wave patterns we have been discussing throughout this video. But here is the thing that most people do not fully appreciate, and it is the key to understanding everything that is about to unfold over the next 12 months. The jet stream does not just respond to El Nino the way a thermostat responds to a temperature change. El Nino does not nudge it slightly. El Nino does not push it a degree or two off its normal course and leave everything else intact. El Nino fundamentally rewires it. The entire planetary circulation gets reorganized from the tropics outward, and the consequences of that reorganization reach into every corner of the globe. Here is the mechanism. During a strong El Nino event, the warming in the tropical Pacific acts as an enormous heat source injected directly into the base of the global atmospheric circulation system. The Hadley cell, the large-scale tropical circulation pattern where warm, moist air rises near the equator, flows poleward at altitude and descends in the subtropics, expands and intensifies in response to that additional tropical heat. That expansion is not subtle. It pushes the subtropical jet stream, the southern branch of the jet, the one that governs weather across the southern United States, stronger, faster, and further into the mid-latitudes than it would normally penetrate. The result is a more active, more energized river of wind barreling across the southern tier of the country, carrying with it enhanced storm track activity, elevated precipitation, and the conditions for more vigorous and more destructive cyclone development across a broader geographic area than the historical average would suggest. At the same time, the polar jet, the northern branch of the jet stream that typically governs weather across the northern plains, Great Lakes and upper Midwest, does not simply stay in place while the subtropical jet strengthens below it. The two jets interact, and the nature of that interaction determines the specific geographic distribution of the severe weather threat. In some El Nino configurations, the two jets merge or run nearly parallel to each other across the continent, and where they come together you get zones of extreme vertical wind shear, the ingredient that takes a disorganized line of thunderstorms and organizes it into rotating supercells, the kind of storms that produce long-track violent tornadoes. In other configurations, the polar jet retreats northward, while the subtropical jet dominates the pattern, concentrating severe weather activity in regions that sit further north than the climatological corridor and are critically far less prepared for what arrives. The implications for what we're about to see this weekend, and for what the coming months could bring, are direct and significant and cannot be overstated. A strengthened subtropical jet means enhanced vertical wind shear across the southern and central United States on a persistent, sustained basis, rather than in the brief episodic windows that characterize a typical spring season. Wind shear, as we established earlier in this video, is the structural ingredient that organizes convection into the most dangerous storm morphologies. When you take that enhanced shear, already elevated because El Nino is pushing the jet stream harder and further north, and you combine it with the elevated instability that comes from a warmer ocean baseline, record Gulf moisture, and more available latent energy throughout the atmospheric column, what you get is not just a favourable severe weather environment. You get an environment that is primed for repeated, intense, back-to-back severe weather outbreaks across an unusually broad corridor, cycling again and again as long as the atmospheric pattern holds its configuration. And this connects directly to what is already happening over North America right now. The locked-in trough ridge configuration, the deep dip in the jet stream over the western United States, and the persistent ridge of high pressure over the southeast is precisely the kind of blocked, high-amplitude pattern that El Nino tends to amplify and make more stubborn. This is one of the most important and least discussed consequences of strong INSO events. El Nino does not just produce more storms, it produces more atmospheric blocking. It generates high-amplitude Rossby wave patterns that stall and refuse to progress, ridges that build and persist for days or weeks instead of moving through in 48 hours, troughs that dig deep and lock in, pumping cold air and instability into the same geographic corridor repeatedly. The atmosphere, under strong El Nino forcing, becomes less mobile, less dynamic in the sense of progression. Individual weather features linger, accumulate impact, and deliver repeated blows to the same regions before the pattern finally shifts. This is the multi-day outbreak signature, and it is the exact structure we're watching develop in real time this weekend. Not a single storm system moving through and clearing out. Not a one-day severe weather event that resets by morning, but a pattern that establishes itself, locks in, and delivers 4 consecutive days of tornado-producing, hail-dropping, wind-driven convection to the same corridor from Texas to Minnesota before the jet stream finally relents. And the critical point, the one I want you to hold on to, is that this pattern is appearing before El Nino has even officially arrived. The ENSO transition is still underway, the Pacific has not yet fully flipped, and the atmosphere is already behaving as if the rewiring has begun. Now I want to introduce a concept that atmospheric researchers have been examining with increasing urgency, because it changes how you should think about what a strong El Nino year actually feels like from the ground. The concept is storm clustering. In a warmer El Nino-influenced atmosphere, severe weather does not simply become uniformly more frequent everywhere across the country. The distribution does not smooth out into a modest background increase that everyone experiences equally. Instead, it clusters. It concentrates into specific corridors during specific windows of vulnerability, hitting those corridors hard and repeatedly while leaving adjacent regions relatively untouched. The variability does not diminish, it sharpens. What you get is not a slightly elevated risk spread evenly across the map. You get intense, concentrated bursts of extreme weather in specific zones, separated by periods of relative quiet, and then another burst in the same zone before the first one has fully processed. The reason this matters practically, and the reason it is so much more dangerous than a uniform increase in storm frequency, is compounding. When severe weather hits the same region 3 or 4 times over a period of 2 weeks, the damage is not additive, it is multiplicative. The first event damages infrastructure, stresses emergency response systems and displaces people. The second event hits before repairs are made, before resources are restocked, before communities have had time to assess and respond. The third event finds a region that is already degraded, already exhausted, already operating beyond its designed capacity for absorbing disruption. The accumulated impact of 3 moderate events hitting the same corridor in rapid succession can vastly exceed the impact of those same 3 events spread across different regions over several months. Infrastructure does not get time to recover. Communities do not get time to rebuild. Insurance systems do not get time to process claims and restore coverage. The compounding effect is what transforms a difficult severe weather season into a catastrophic one, and it is precisely the clustering dynamic that El Nino tends to produce. The northward displacement of the severe weather corridor is another signature of jet stream modification under ENSO influence, and it deserves specific attention because it carries a consequence that goes beyond meteorology into preparedness. As the subtropical jet strengthens and pushes further into the mid-latitudes, it carries the severe weather environment with it. The tornado corridor, which climatologically is centered across Oklahoma, Kansas, and northern Texas, shifts northward. Regions that historically sit above the main zone of tornado risk find themselves inside it. Minnesota in early April is the example we flagged earlier, and it is not a coincidence or a statistical anomaly. It is a direct expression of a jet stream that has been pushed northward by El Nino-driven circulation changes. And the communities that find themselves newly inside that expanded risk envelope are, by definition, less prepared for it. They have less experience with violent tornadoes. Their building codes may not reflect a high tornado risk. Their emergency management systems are calibrated for a threat level that no longer matches what the atmosphere is delivering. The geographic expansion of risk is not just a weather story. It is a preparedness and infrastructure story. There is one additional layer to the jet stream picture that I want to address briefly, because it adds important complexity, even if it does not change the fundamental direction of the argument. Arctic amplification, the well-documented phenomenon of the Arctic warming 2 to 4 times faster than the global average, has been hypothesized by a growing body of researchers to weaken the west-to-east flow of the polar jet stream. The mechanism is straightforward. As the Arctic warms faster than the mid-latitudes, the temperature contrast between pole and mid-latitude decreases, and a weaker temperature gradient produces a weaker, more meandering jet stream that is more prone to the high-amplitude wave patterns and blocking events we have been discussing. The scientific debate on the precise magnitude of this effect is genuine and ongoing, but the implication, if the hypothesis holds, is that two separate forcing mechanisms, tropical warming from El Nino pushing the subtropical jet harder, and Arctic warming weakening the coherence of the polar jet, could be simultaneously pushing the jet stream configuration toward more extreme, more persistent, more impactful wave patterns. Not one driver, two drivers, both pointing in the same direction. What I want you to carry forward from this section is not a collection of technical details about atmospheric dynamics. It is a single, clear understanding of what is actually happening and why it matters. The jet stream is not a passive feature that El Nino adjusts slightly before the atmosphere returns to normal. It is a dynamic, planetary scale system that El Nino can fundamentally and persistently reorganize. When that reorganization happens on a planet already carrying record baseline temperatures, with record ocean heat content, with record Gulf moisture feeding storm systems from below, the resulting weather patterns are more amplified, more stubborn, more geographically expansive, and more concentrated in their impacts than anything in the historical El Nino record would predict. The multi-day outbreak structure beginning this weekend, the locked-in pattern, the repeated convective cycling, the northward displaced tornado corridor, the broad geographic envelope of simultaneous risk, is what jet stream rewiring looks like when it is just getting started. But the storms are only one expression of what this rewiring produces. The same jet stream architecture that is about to deliver 4 days of tornadoes to the Central Plains is simultaneously creating entirely different and equally dangerous conditions in other parts of the country. A pattern that floods one region drains another. What arrives with the storms is not a single hazard. It is a geography of simultaneous, divergent, compounding extremes. Flood in one corridor, fire in another, freeze somewhere else, all driven by the same locked-in atmospheric structure, all happening at the same time, all demanding response from systems that were never designed to handle all of them at once. That is where we are going next. Part 9. Coupled extremes. Flood, fire, freeze. The same jet stream pattern that is about to deliver 4 days of severe weather to the central United States is simultaneously creating entirely different hazards in other parts of the country. And this is one of the most underappreciated aspects of amplified atmospheric patterns, one that rarely gets the attention it deserves in standard weather coverage. Because standard weather coverage focuses on one storm system at a time, one threat zone at a time, one headline at a time. But the atmosphere does not operate that way. It does not produce a single type of extreme and leave everything else alone while that extreme plays out. Under amplified forcing, it fractures. It splinters into a geography of divergent, simultaneous, opposing conditions, all driven by the same underlying architectural feature, all expressing themselves at the same moment, all demanding response from systems that were never designed to handle all of them at once. To understand what that means in practice, you need to look at the full map, not just the storm corridor from Texas to Minnesota, the entire continental picture. Because what is happening on either side of that corridor is just as significant as what is happening inside it, and the combination of all three zones simultaneously is what makes this pattern something qualitatively different from a standard severe weather outbreak. Start southeast of the storm corridor. The ridge, that persistent bulging area of high pressure anchored over the southeast, is not simply a passive feature sitting quietly while the storms do their work to the northwest. It is actively doing something, and what it is doing is suppressing. Under a persistent ridge, the atmosphere stabilizes from above. The cap strengthens. Convection cannot develop. Skies clear and stay clear. Temperatures climb and keep climbing. And the longer that ridge holds its position, which, under El Nino-driven blocking, it is inclined to do, the more aggressively it dries out the region beneath it. Soil moisture depletes, vegetation stress accumulates, stream flows decline, and the fuels that would carry a wildfire, the grasses, the leaf litter, the understory brush, progressively lose their moisture content until they reach the threshold where all they need is a spark and a wind event to become a catastrophe. The southeast and the southern Appalachian region have been running abnormally dry for weeks. That is not a new development. It is a pre-existing vulnerability that the current atmospheric pattern is now amplifying and extending. A persistent ridge amplification does not just maintain that dryness, it intensifies it. Warm temperatures accelerate evaporation from soils that are already depleted. Dry air pulls residual moisture from vegetation, and the wind events that accompany the pressure gradient between the ridge and the adjacent storm systems provide exactly the kind of rapid spread fire weather conditions that turn a local brush fire into a regional disaster. The same jet stream configuration that is delivering tornadoes to Kansas is simultaneously creating active fire weather conditions across the Carolinas, Tennessee, and the southern Appalachian highlands. Not as a coincidence, not as two separate unrelated events happening to occur at the same time, as two direct and simultaneous expressions of the same locked-in atmospheric architecture. Now look to the west, because the picture there is equally complex and in some ways more consequential for the long-term resource picture. The trough, the deep dip in the jet stream anchored over the western United States, is pulling cold air southward and driving precipitation events into the western mountain ranges. In the immediate term, that means late-season snowfall across mountain ranges that may or may not have the capacity to absorb and store it effectively. But the immediate snowfall is not the issue. The issue is timing, temperature, and variability, and in all three dimensions, the current pattern is delivering exactly the wrong combination for Western water management. Western snowpack is not simply a meteorological metric. It is the primary water storage system for much of the western United States. The mountains serve as a natural reservoir, accumulating snow through winter and spring, then releasing it gradually through summer as temperatures warm and snowmelt feeds rivers, replenishes aquifers, and fills the reservoirs that supply agriculture and municipalities across an enormous geographic footprint. That system depends on cold, steady precipitation events that build snowpack incrementally and a gradual warming curve that releases it in a controlled, manageable flow. What the current atmospheric pattern and what El Nino-driven volatility more broadly tends to produce instead is exactly the opposite. Precipitation arrives in intense bursts separated by dry periods. Atmospheric river events dump enormous quantities of water in short windows. Temperature swings cause warm storms to deliver rain instead of snow at elevations where snow is needed, or trigger rapid melt cycles that release water too fast for reservoir systems to capture and store. The boom-bust cycle of mountain hydrology accelerates, and the infrastructure designed for gradual, predictable snowmelt gets overwhelmed by an erratic, volatile delivery schedule that it was never engineered to handle. The result is a paradox that plays out across the western United States in strong ENSO years. Flooding in mountain valleys during intense precipitation events followed by water scarcity downstream during the dry season because the snowpack that should have provided steady summer flow was either never built up adequately or was released all at once during a mid-spring melt event. Too much water at the wrong time in the wrong form, arriving too fast followed by not enough water when crops need it most. This is what atmospheric fragmentation means at a practical operational level. The jet stream, under amplified El Nino forcing, does not simply shift weather patterns in a coherent direction that allows systems to adapt. It fractures them into simultaneous, divergent, geographically separated extremes that each demand independent, immediate response while sharing the same finite pool of resources, personnel, and institutional attention. You cannot respond to catastrophic flooding in Iowa with the same emergency management resources you are simultaneously deploying to fight wildfires in North Carolina. You cannot address a snowmelt crisis straining Colorado reservoir infrastructure, while your water management agencies are also managing flood control operations in the Central Valley of California. Each crisis is real, each demands full attention, and when they arrive concurrently, the capacity of every system involved, emergency management, infrastructure, agriculture, supply chains, gets stretched toward and sometimes beyond its breaking point. The agricultural implications of this fragmentation deserve particular emphasis because they connect this weekend storm corridor directly to the food supply consequences we will examine in the next section. Agricultural systems in the United States are geographically distributed for reasons that reflect decades of calibration between crop type, climate zone, and infrastructure. Corn and soybean production in the Midwest is matched to the precipitation and temperature regime of that region. Wheat production on the southern plains is calibrated to its specific seasonal pattern. Western specialty crops depend on predictable water delivery from snowmelt-fed irrigation systems. When the atmosphere fragments, when the Midwest gets hammered by repeated flood-producing storm events, while the Southeast bakes under a persistent drought ridge, and the West swings between atmospheric river flooding and water storage deficits, the agricultural calendar gets disrupted across multiple production zones simultaneously. Planting is delayed in fields that are still saturated from the previous week's storm cycle. Soil temperatures in flooded fields drop back below germination thresholds, pushing planting windows past the optimal dates and compressing the growing season from the front end. Simultaneously, crops in ridge-dominated regions face heat stress and moisture deficits during critical growth stages. Irrigation demand spikes in regions where water managers are already concerned about reservoir levels. The timing mismatches compound across the season, and by the time the critical pollination and grain fill windows arrive in summer, multiple production zones have accumulated deficits that translate directly into yield reductions. Individual field-level problems aggregate into regional production shortfalls. Regional shortfalls aggregate into national supply disruptions. And national supply disruptions in the world's largest agricultural economy propagate into global commodity markets with consequences that reach far beyond American borders. The infrastructure stress dimension compounds everything further. Each severe weather event that damages roads, bridges, rail lines, and grain handling facilities reduces the system's capacity to respond to the next event. Each flood that delays spring planting pushes harvest later into fall, increasing the risk that the harvest itself gets disrupted by early autumn weather events. Each wildfire that damages transmission infrastructure or forces evacuations of agricultural labour reduces production capacity in ways that take months or years to fully restore. The cumulative degradation of response capacity is itself a form of damage, invisible in any single event's damage assessment but very real in its aggregate effect on the system's resilience. The current outbreak is not an isolated event. It is the first visible expression of a fragmented atmospheric pattern that, if it persists and intensifies as El Nino continues its development over the coming months, will produce simultaneous, divergent, compounding extremes across the United States and eventually across the globe. Because El Nino does not stop at the American border, it does not confine its jet stream rewiring to North America. It reorganizes the entire planetary circulation, and the fragmentation of extremes that begins this weekend in the United States is the local expression of a global pattern that will express itself differently but equally severely across every continent on Earth. The storms are the beginning. The locked-in jet stream is the mechanism. And the food supply chain is where this story stops being about weather and starts being about the daily lives of billions of people. That is where we are going next. Part 10. agricultural stress chain reaction. The global food system is one of the most climate-sensitive economic structures on the planet. It is also one of the most consequential. When it functions, it is invisible. Food moves from fields to markets to tables across thousands of miles of supply chain infrastructure so efficiently and so reliably that most people in wealthy nations never think about it. When it fails, or even when it strains, the consequences reach into every household on Earth with a directness and speed that no other economic disruption can match. You can absorb a disruption to semiconductor supply chains. You can navigate a shipping bottleneck. You cannot negotiate with hunger. El Nino is the single most powerful natural disruption the global food system faces. Not because any individual El Nino event necessarily causes famine, the system carries buffers and redundancies that absorb significant stress, but because El Nino has a capability that no other natural climate phenomenon possesses to the same degree. It can stress multiple major agricultural production zones simultaneously, not sequentially, not one after another, in a way that allows recovery between shocks, simultaneously, all at once. And it is precisely that simultaneity, that synchronized multi-region pressure on the global food supply, that food security researchers identify as the scenario they fear most. To understand why, you need to think about global agriculture not as a collection of national food systems operating independently, but as an interconnected network of production zones, each contributing to a global pool of supply that the entire world draws from. Australia is one of the world's largest wheat exporters, and its production sits squarely in the Western Pacific influence zone, where El Nino characteristically brings drought conditions, reduced rainfall, elevated temperatures, and the kind of prolonged dryness that turns wheat-growing regions into dust. India produces enough grain to feed more than 1 billion people, and its agricultural system is built around the monsoon, a seasonal rainfall pattern that El Nino can weaken, delay, or in severe cases nearly suppress, with consequences that cascade through the entire subcontinent's food production. Southeast Asia's rice paddies supply a significant fraction of global rice production, and they are sensitive to both the direct temperature effects of Pacific warming and the indirect disruption of monsoon circulation patterns across the region. And the Americas, the United States, Brazil, Argentina, collectively produce the corn, soybeans, and wheat that anchor global feed and food supply chains, serving as the backstop that the rest of the world depends on when other production zones underperform. In a normal year, this geographic distribution of production is the system's greatest strength. If one region has a bad season, the others compensate. Australia endures a drought, but India has a strong monsoon, and global markets adjust, prices move modestly, supply chains reroute, and the system absorbs the shock without visible rupture. This is the buffer that has made the modern global food system remarkably resilient to individual regional disruptions. Geographic diversification of production is the insurance policy that the world has been quietly relying on for decades. El Nino threatens to cancel that insurance policy simultaneously across multiple regions. During a strong El Nino event, the teleconnection pattern, the mechanism by which tropical Pacific warming ripples outward through the global atmospheric circulation and reshapes weather patterns on every continent, does not confine its effects to a single breadbasket. It reaches all of them, often at the same time, often in the same direction. Australia dries out, the Indian monsoon weakens, Southeast Asian precipitation patterns shift away from the rice-growing regions that depend on them, and the Americas face their own El Nino-driven disruptions, which, in the United States, express themselves as exactly the kind of fragmented atmospheric pattern we have been describing throughout this video. Repeated severe weather in agricultural regions, flooding that delays planting, heat stress under persistent ridges, and the timing disruptions that compound across the growing season into measurable yield reductions. This is what researchers call multi-breadbasket exposure, and it is the food security scenario that sits at the top of every serious risk assessment of El Niño's global consequences. The concern is not a crop failure in one region. The global system can absorb that. The concern is simultaneous yield reductions across 3 or 4 major production zones at the same time, even modest reductions, even 5 to 7% below normal in each zone individually, because when those reductions occur together, their combined effect on global supply is not additive. It is multiplicative. The buffer disappears. The compensation mechanism fails. Global reserves, which have been trending downward as a percentage of annual consumption for years, get drawn down rapidly. And prices, the most sensitive and immediate signal in any commodity market, spike in ways that propagate through the entire food system with a speed that catches consumers, governments, and institutions off guard every single time. Here is where the warmer baseline we discussed earlier becomes specifically and urgently relevant to food. The 1997-98 El Nino caused significant and well-documented agricultural disruptions. Australian wheat production dropped sharply, Indonesian palm oil yields fell, the Indian monsoon underperformed, multiple Southeast Asian economies faced food price pressures that contributed to social instability. But all of that happened on a global baseline temperature that was measurably cooler than today's. Crop varieties in use at that time were adapted to the temperature ranges of the late 20th century. The thermal buffers, the gap between average growing season temperatures and the stress thresholds above which yields begin to decline sharply, were wider than they are now. Today, after 3 decades of additional warming, many of the world's most important agricultural regions are already operating significantly closer to those thermal stress thresholds. Rice, wheat, and maize, the 3 crops that together provide the majority of calories consumed by the global population, all have well-characterized temperature sensitivity windows during which heat exposure causes irreversible yield losses. Pollination fails, grain fill is truncated, protein content drops, and warming over the past 3 decades has pushed the average growing season temperatures in many critical production regions measurably closer to those upper boundaries, leaving a narrower margin before stress begins. An El Niño-driven heat event on today's baseline does not push crops to the same stress level that an equivalent event would have caused 30 years ago. It pushes them further because the starting point has already moved toward the danger zone, and the additional El Niño forcing is applied on top of a baseline that has already consumed much of the available buffer. The historical record offers guidance, but no longer sets the ceiling. The 2015-16 El Niño, the most recent strong event and one of the most powerful in the observational record, contributed to severe drought conditions across southern Africa, reduced agricultural output across multiple Southeast Asian nations, and coincided with food price spikes in vulnerable import-dependent markets. That event's agricultural consequences were significant and well documented, and it occurred on a baseline that was cooler than today's, with crop systems that had marginally more thermal headroom than they currently possess. The next strong El Niño arrives on a hotter planet, against a backdrop of food systems that are more tightly integrated, more globally traded, and operating closer to their biophysical limits than at any previous point in the observational record. The cost structure of food production amplifies the vulnerability in ways that are less visible, but equally important. El Niño-driven droughts in key agricultural regions increase irrigation demand as rainfall deficits force farmers to compensate with groundwater and surface water withdrawals. Increased irrigation demand drives up energy costs for pumping, which are already elevated in many regions by other climate-driven factors. At the same time, natural gas market disruptions, which can be triggered by weather-driven demand spikes in winter heating or summer cooling, and which are further complicated by geopolitical factors that do not pause during El Niño events, feed directly into nitrogen fertilizer production costs, since fertilizer manufacturing is among the most energy-intensive industrial processes on Earth. The result is that farmers in stressed regions simultaneously face reduced yields and increased production costs. A margin compression that propagates through the food system with a lag of several months, showing up in grocery prices and food assistance program costs long after the drought or flood that caused it has faded from the news cycle and been replaced by the next crisis. This lag is one of the most dangerous features of climate-driven food system disruptions, and it is one that political and economic systems consistently fail to anticipate. A severe weather event hits an agricultural region in April. The planting disruption affects yields measured in October. The harvest shortfall reaches commodity markets in November. Retail food prices begin reflecting the supply reduction in January or February of the following year. By that point, the connection between the original weather event and the price at the checkout counter is invisible to most consumers and inconvenient for most policymakers. The disruption has been absorbed into the background noise of economic volatility, attributed to other causes, and the systemic link between atmospheric physics and household food budgets goes unexamined. The humanitarian dimension of this chain is stark and should not be abstracted into economic language that obscures its human reality. The regions that face the most severe consequences of El Niño-driven food price increases are not the wealthy import-dependent nations that can buffer price shocks through fiscal policy, food assistance programs, and diversified supply chains. They are the regions where food expenditure constitutes the majority of household income, parts of sub-Saharan Africa, South Asia, the Pacific Islands, and the Horn of Africa, where populations already living at or near nutritional margins have no buffer to absorb even modest price increases. A 5% increase in global wheat prices is a rounding error in a grocery budget in a wealthy nation. In a country where half the population spends 60% of its income on food, the same 5% price increase is not an inconvenience. It is a hunger event. It forces substitutions, reduces meal frequency, pulls children out of school to contribute to household income, and in the most vulnerable populations tips nutritional status from stress to acute. Every link in this chain, the multi-breadbasket exposure, the baseline temperature amplification, the cost cascade from drought through fertilizer, through retail prices, the humanitarian concentration of risk in the most vulnerable populations, traces directly back to the same interconnected system that is producing tornado warnings across the central United States this weekend. The atmospheric energy loading the storm corridor from Texas to Minnesota, the Pacific Ocean dynamics driving the ENSO transition beneath the surface, the jet stream rewiring that is distributing simultaneous divergent extremes across the continental map. It is all one system. The storms are local and immediate. The food supply consequences are global and months away. But the distance between them is shorter than it appears, and the chain connecting them is already in motion. The atmospheric pattern does not stop at the supermarket. It reaches further into commodity trading floors, into central bank policy meetings, into the financial models that institutional investors use to price risk, in a world where climate variability has become an unavoidable macroeconomic input variable. And that is where this story moves next. Because what is building in the Pacific right now is not just a weather event, and it is not just a food supply event. It is a potential economic event, and the distance between a locked-in jet stream over Kansas and a policy crisis in a finance ministry on the other side of the world is shorter than almost anyone in either of those rooms currently understands. Part 11. Economic Transmission Layer. Weather has always been an economic variable. Droughts raise food prices, floods damage infrastructure, storms disrupt supply chains. These are not new dynamics. Civilizations have grappled with the economic consequences of weather since the first grain was harvested and stored. What is new is the scale and speed at which climate-driven disruptions can propagate through a globally interconnected economy, and the degree to which a strong El Niño event on an elevated baseline can amplify those transmission pathways in ways that previous generations never had to contend with. Start with commodity markets, because they're the most direct transmission mechanism. Wheat, rice, corn, soybeans, palm oil, these are globally traded commodities whose prices respond to production forecasts, and production forecasts respond to weather. When El Niño disrupts grain production in Australia, rice production in Southeast Asia, and soybean planting conditions in South America simultaneously, the global commodity markets don't just register individual price increases. They register correlated increases across multiple staples at the same time. Portfolio diversification doesn't help when all the crops are stressed at once. Commodity traders who might ordinarily hedge exposure in wheat with positions in corn, or balance Southeast Asian rice exposure against South American soybean production, find that their diversification strategies fail precisely when they are most needed, because the same atmospheric event is stressing all of them in parallel. Historical El Niño events have been associated with measurable commodity price inflation. Estimates vary, but analyses of past strong El Niño events suggest an average commodity price increase on the order of 5% during the event year, with certain commodities, particularly rice and palm oil, spiking significantly higher depending on the geographic distribution of impacts. The 2015 to 2016 event coincided with notable commodity market disruptions, and the 1997 to 1998 event produced even more pronounced effects, with rice prices in some Asian markets rising by 30% or more in the months following peak El Niño conditions. The 1982 to 1983 event, one of the most powerful on record at the time, contributed to agricultural output collapses across multiple continents simultaneously. What's important to understand is that these events didn't just shock one market in one region. They reconfigured the entire global supply picture for multiple commodities at the same time, leaving importing nations exposed and export-dependent economies destabilized. But commodity prices don't exist in isolation. They're coupled to energy markets through transportation costs and fertilizer production. Fertilizer prices track natural gas prices, which themselves are sensitive to weather-driven demand. A cold winter in Europe or a hot summer in Asia increases energy demand for heating or cooling, which competes with industrial demand for fertilizer production, which drives up fertilizer costs, which increases the cost of food production, which adds to food price inflation. These coupling mechanisms mean that a climate disruption doesn't just affect the crop that was directly impacted, it ripples through the cost structure of agricultural production globally. Nitrogen fertilizer, which is synthesized from natural gas, is a critical input for virtually every major grain crop. When energy prices rise in response to weather-driven demand spikes, the cost of nitrogen fertilizer rises with them. Farmers who planted their crop with one set of input cost assumptions find their margins compressed by the time harvest arrives. Some reduce fertilizer application to manage costs, which reduces yields, which further tightens global supply. Others simply don't plant. Either way, the downstream consumer pays, and this is where central banks start paying attention. Food price inflation is a significant component of consumer price indices in virtually every economy. In advanced economies, food typically represents 15 to 20% of the household consumption basket. In emerging markets, that share can be 40% or higher. When food prices spike, headline inflation rises, and central banks face a dilemma. Do they tighten monetary policy to control inflation, risking an economic slowdown, or do they accommodate the price increase as transitory, risking inflation expectations becoming unanchored? During previous El Nino events, this tension was real but manageable, because the inflationary impulse from food prices was partially offset by stability in other sectors, and because the global economy was not simultaneously contending with elevated debt levels, fragile supply chains still recovering from prior disruptions, and geopolitical instability that reduces the flexibility of major producers to step into supply gaps. On a warmer planet, with a stronger El Nino superimposed on a higher temperature baseline, the food price impulse could be larger, the duration longer, and the geographic breadth wider. Central banks in emerging market economies, where food constitutes a larger share of the consumer basket, and where currency vulnerabilities can amplify imported inflation, would face particularly acute pressure. Import-dependent nations that lack significant foreign exchange reserves may be unable to sustain the cost of importing food at elevated global prices without drawing down critical buffers or allowing currency depreciation, which further raises the cost of imports. The policy space narrows, the trade-offs become sharper. And the political consequences of food price inflation, historically one of the most reliable triggers of social unrest, add a governance dimension to what began as an atmospheric event over the Pacific Ocean. Supply chain amplification adds another layer of complexity. Modern food supply chains are optimized for efficiency, not resilience. Just-in-time logistics minimize storage costs, but also minimize buffers. Warehousing has been systematically squeezed out of the system over decades of supply chain optimization, driven by financial metrics that prioritize capital efficiency over operational robustness. When a disruption occurs, a port closure due to flooding, a harvest delay due to heat stress during pollination, a transportation bottleneck due to infrastructure damage, the effects propagate quickly because there's no slack in the system. There is nowhere to absorb the shock. Multiple simultaneous disruptions, which is precisely what a strong El Nino can produce across multiple continents, can overwhelm the system's capacity to reroute and adapt. The system was never designed to handle correlated shocks of this magnitude, because for most of the period during which modern supply chains were engineered and refined, such shocks were rare enough to be treated as negligible tail risks. The lag between weather event and price shock is typically 3 to 6 months, and this temporal gap matters enormously for how these events are understood and responded to. A planting disruption in April affects yields in September, which affects harvest volumes in October, which affects futures markets in November, which affects grocery prices in January. This lag creates a false sense of calm in the immediate aftermath of a weather event. The storms hit, the news cycle moves on, officials declare the situation managed, and then months later, the economic consequences arrive with full force. By that point, the connection to the original atmospheric event has been largely forgotten by the general public and by most policymakers. It becomes simply inflation, or supply chain issues, or market conditions, stripped of its meteorological origins. But the origin is there, and it's direct, and failing to trace the causation back to its source means that the policy response is often miscalibrated. Monetary tightening applied to inflation that is fundamentally supply-side and climate-driven may reduce demand, but it cannot produce rain in a drought region or undo a failed harvest. Understanding that lag also means understanding something important about the decision window. The time to build supply buffers, to diversify sourcing, to shore up balance sheet resilience, and to coordinate policy responses is not after the price spike arrives. It is now, when the atmospheric conditions are still developing, when the El Nino pattern is still consolidating, when there is still time for institutional actors, governments, multilateral organizations, commodity traders, food manufacturers, central banks, to position themselves ahead of the disruption rather than react to it after the damage is done. The 4-day outbreak rolling across the central United States this weekend may seem like a local weather story. Tornadoes in Kansas, hail in Oklahoma, wind damage in Iowa, infrastructure damage tallied in local news, insurance claims processed, communities beginning the work of recovery. But the atmospheric system producing it, the amplified jet stream, the Pacific-driven forcing, the seasonal energy compression that concentrates severe weather potential into narrow geographic corridors, is the same system that, scaled up over the coming months by a strengthening El Nino, could inject significant and sustained inflationary pressure into global commodity markets, stress supply chains that are already operating with insufficient buffer capacity, and create macroeconomic headwinds that reach into every economy on Earth. The scale difference between a tornado outbreak in the Great Plains and a full El Nino-driven global disruption is enormous, but the atmospheric physics connect them. The same oceanic heat anomaly in the central and eastern Pacific that can redirect jet streams and produce severe weather in North America can simultaneously suppress monsoon rainfall in South Asia, generate drought conditions across Australia and Southern Africa, and destabilize precipitation patterns across Central America. These are not independent events. They are expressions of the same underlying system state, playing out across different geographies on different timescales. Weather isn't just weather anymore, it hasn't been for a while, but the institutional frameworks for pricing, planning, and responding to weather risk have not kept pace with the reality. It is a macroeconomic input variable that central banks, finance ministries, and institutional investors are only beginning to incorporate into their models with the seriousness it deserves. The frameworks for thinking about climate risk in economic terms remain underdeveloped. The data pipelines connecting meteorological forecasting to economic scenario planning remain inadequate, and the political incentives to plan for low-probability, high-impact events remain weak in most governance systems. The El Nino that may be building in the Pacific right now is not merely a climate event. It is a potential economic event, a potential food security event, a potential political stability event, and a potential public health event, because the consequences of food price inflation and supply disruption are not distributed evenly across society, and the distance between a storm in Oklahoma and a price spike in a market half a world away is shorter than most people think, and growing shorter with every additional link added to the global supply chain, every additional increment of warming added to the baseline, and every additional year that institutional preparedness lags behind the evolving risk profile. The question is how severe it gets. Whether the El Nino now developing peaks at moderate intensity or pushes into strong or extreme territory will determine a great deal about the magnitude of the economic consequences that follow. Whether the disruptions concentrate in one region or distribute across multiple continents simultaneously will determine whether global markets can rebalance or become overwhelmed. Whether policymakers begin positioning now or wait for the price signals to arrive will determine whether the response is proactive or reactive, calibrated or panicked. And the honest answer is, we don't know with precision. Atmospheric forecasting has improved dramatically, but the nonlinear dynamics of a warming ocean interacting with a warming atmosphere interacting with a globally interconnected economy, produce outcomes whose tails are wider than our models comfortably acknowledge. The uncertainty itself is information. It tells us that the case for building resilience, deepening buffers, and taking the risks seriously is not contingent on knowing exactly how bad it gets. It is sufficient to know that the range of outcomes includes some that are very bad indeed, and that the cost of preparation is considerably lower than the cost of the disruption it is designed to absorb. That calculation, more than any specific forecast, is the one that should be driving decisions right now. Part 12. The Uncertainty Envelope. I've spent this entire video building a case that the multi-day severe weather outbreak hitting the United States is connected to a larger Pacific-driven climate transition, that the El Nino developing beneath the surface of the equatorial Pacific could be powerful and consequential, and that the atmospheric, agricultural and economic effects over the next 12 months could be severe. I've walked through the commodity transmission mechanisms, the central bank dilemmas, the supply chain fragility, and the lag between weather event and economic consequence. I've argued that what looks like a regional severe weather story is actually the opening movement of something much larger. All of that may be correct. The evidence supports the direction of the argument, but I owe you the uncertainty, because the uncertainty is real, and ignoring it, glossing over it in the interest of narrative momentum, would make this video dishonest. You deserve the full picture, including the parts that complicate the story I've been telling. ENSO may peak weaker than the model ensemble suggests. The spring predictability barrier is a real and well-documented phenomenon in atmospheric science, and forecasts made in April carry genuine ambiguity about conditions in October. The atmosphere-ocean system in the tropical Pacific goes through a phase each spring where its future trajectory is particularly difficult to pin down, where initial conditions are less informative about what comes next, and where model skill drops noticeably compared to forecasts made in other seasons. This isn't a flaw in the models that better computing will eventually fix. It's a fundamental feature of the system's dynamics. The subsurface heat loading in the Pacific, while genuinely suggestive of a strong event, could dissipate or be redistributed through oceanic processes in ways that produce a moderate El Nino rather than a historically extreme one. Kelvin waves can propagate heat that does not ultimately surface in the way the thermocline anomalies suggest. Models have overestimated ENSO development before, particularly in transitional years when the ocean-atmosphere coupling is noisy, when the Walker circulation response is sluggish or ambiguous, and when the initial conditions that should be driving the signal are competing with internal variability that pushes in the other direction. The 2014 event is the cautionary tale that every serious ENSO forecaster carries with them. That year, subsurface conditions looked remarkably similar to the setup for a major El Nino. Models were bullish, the scientific discussion was serious and sustained, and then the atmospheric coupling never fully materialized. The ocean loaded the gun, but the atmosphere didn't pull the trigger with the sustained westerly wind bursts needed to lock in the feedback loop. The result was a weak and disappointing El Nino that underperformed virtually every early season forecast. The lesson wasn't that subsurface heat loading is uninformative, it is informative. The lesson was that the ocean's readiness is necessary but not sufficient. The atmosphere has to respond, couple, and sustain the feedback. And that process is less predictable than the oceanic precursors alone would suggest. The atmospheric coupling between ENSO and mid-latitude weather patterns could also develop differently than the strongest scenarios suggest. Teleconnections, the statistical relationships between tropical Pacific sea surface temperature anomalies and weather patterns in distant regions, are probabilistic tendencies, not deterministic laws. They represent what the atmosphere tends to do when forced by a given ENSO state, averaged over many events, smoothed across decades of observation. But any individual El Nino event plays out in an atmosphere that is simultaneously being shaped by the Arctic Oscillation, the Madden-Julian Oscillation, the Pacific Decadal Oscillation, stratospheric dynamics, and a dozen other modes of variability that interact in ways that no operational forecast model resolves with full fidelity. A strong El Nino usually amplifies the jet stream, displaces the storm track, and enhances severe weather environments across parts of the United States. But the specific configuration in any given year, which corridors see the enhanced risk, when the peak activity occurs, how persistently the jet locks into amplified states, depends on the superposition of all those interacting variables. The severe weather season could, in a less favourable ENSO configuration or a less favourable phasing of other oscillatory modes, decouple from the Pacific forcing and evolve in ways that are less extreme than what we'd expect from a canonical strong El Niño response. The nonlinear feedbacks could go either way. This is perhaps the most important and least comfortable piece of intellectual honesty in the whole analysis. In a system as complex as the global climate, feedbacks can amplify, making outcomes worse than linear projections, producing effects that exceed what you'd calculate by simply scaling up the ENSO signal by baseline warming, or they can dampen, moderating the response in ways that aren't captured in the forcing alone. The warmer baseline makes amplification more likely in most theoretical frameworks. A warmer atmosphere holds more moisture, which means more latent heat release available to power convective systems. Warmer sea surface temperatures and source regions for severe weather increase the thermodynamic fuel available. These are real physical mechanisms that operate in the direction of amplification. But the real atmosphere doesn't always conform to theoretical frameworks. Internal variability is large enough to obscure forced signals, especially on the timescales and spatial scales relevant to individual seasons. Confidence in the direction of change is well supported. Confidence in the magnitude is much less so, and anyone telling you otherwise is overstating what the science actually delivers. All of that said, and it needed to be said clearly and without hedging, this uncertainty does not reduce the significance of what we're observing right now. The 4-day outbreak is real. The atmospheric anomalies driving it are real. The subsurface Pacific heat loading is real. The elevated baseline temperature is real, not a projection or a model artifact, but a measured fact confirmed by every major global temperature dataset. The directional evidence points toward a consequential ENSO event, developing on a planet whose thermal baseline has no historical precedent in the observational record. The uncertainty is about magnitude and timing, not about whether the system is moving. It is moving. The question is, how far and how fast it goes, and those are genuinely open questions, open enough to warrant humility, not open enough to warrant complacency. Probabilistic framing is the honest way to present all of this. The probability of a significant El Niño developing over the next 6 to 9 months is high. Most model ensembles place it well above 70%, and the oceanic precursors are consistent with that assessment. The probability of a historically extreme event, something approaching or exceeding the magnitude of 1997 to 1998, is lower but non-trivial. Credible estimates put it in the range of 20 to 35% depending on the model and the metric used. Those numbers are not alarming in isolation, but the consequences of El Niño scale non-linearly with intensity. The difference between a moderate event and a strong event is not a proportional difference in outcomes. A strong event doesn't just produce more of what a moderate event produces. It triggers threshold crossings, cascade failures, and tipping points in agricultural, hydrological, and social systems that a moderate event never reaches, and the elevated baseline ensures that even a moderate El Niño will produce effects that exceed what the same magnitude event would have produced on the cooler planet of 30 years ago. The same ENSO anomaly, superimposed on a warmer background state, produces more intense rainfall, more severe drought, more extreme heat, and more energetic storm systems. The intensity of the event and the intensity of the planet are multiplying together, not adding. The storms this weekend are a data point. They are consistent with the hypothesis that the atmosphere is already responding to Pacific forcing, that the jet stream is already in the kind of amplified configuration associated with early season ENSO teleconnections. They are not proof of that hypothesis. Severe weather outbreaks happen every spring. This one would need to be placed in the context of the full atmospheric state, the subsurface oceanic conditions, the model forecasts, and the observed ENSO trajectory before it could be elevated from consistent with to evidence for. But it is a signal worth paying attention to, because if the trajectory continues, the next 12 months will deliver more signals and eventually confirmations that the system we're living in has entered a new state of operation, one where what used to be the upper tail of natural variability is becoming the new centre of gravity. Imagine standing in a field in central Kansas this Saturday evening. The sky to the west has turned that particular shade of green that experienced storm watchers recognize immediately. The colour the atmosphere takes on when it's holding more energy than it knows what to do with. When the combination of moisture, instability, and wind shear has loaded the environment to a point where convection becomes not just possible but inevitable. The wind has shifted. The temperature has dropped 10 degrees in 15 minutes. The pressure gradient that has been building since midday has finally found its release. And somewhere to the southwest, a wall cloud is rotating with the slow, deliberate intent of a system that has been fed more fuel than it could ever consume in a single afternoon, drawing energy up from a Gulf of Mexico that is running at record warmth, organising that energy through a mesocyclone that is tightening with every passing minute, and preparing to put it back down on the ground in a form that leaves no ambiguity about the forces involved. That storm, and the one behind it, and the one behind that, cycling across the same corridor for 4 consecutive days, not drifting randomly but locked into the same geographic channel by the same planetary scale atmospheric configuration, is not a random event. It is not bad luck, not an anomaly, not a once-in-a-generation coincidence. It is the atmosphere processing energy that was loaded into it by a Gulf of Mexico running at record warmth, organised and directed by a jet stream locked into an amplified configuration by planetary scale wave dynamics that have their roots in the tropical Pacific, and ultimately forced by an equatorial ocean that is in the process of transitioning toward what could be one of the most consequential El Nino events in the observational record. Every component of that causal chain is real, measurable, and physically understood. The uncertainty is in the magnitude of what comes next, not in the reality of what is happening now. The outbreak this weekend is the first chapter of a story that will take 12 months to tell fully. The Pacific subsurface is loaded with heat that has not yet reached the surface. The models are diverging on magnitude but converging on direction, which is itself informative. When models disagree about how much but agree about what, the direction is the reliable signal, and the magnitude is where humility is warranted. The baseline is higher than it has ever been in the period of instrumental observation, which means every event that unfolds in the next 12 months does so on a foundation that has no direct historical analogue. And the atmospheric consequences of those 3 realities, loaded ocean, uncertain models, elevated baseline, are going to express themselves in ways that extend far beyond tornado warnings in the Great Plains, reaching into monsoon systems, agricultural calendars, commodity markets, and central bank policy decisions in ways that most people will never trace back to an evening sky over Kansas. I am not telling you that catastrophe is guaranteed. I want to be precise about that, because precision matters, and because the easiest thing in the world is to let justified concerns slide into unjustified certainty. The uncertainty is real, the models carry genuine ambiguity, and the system could evolve in ways that are less extreme than the worst-case scenarios. But I am telling you that the atmospheric behaviour we are witnessing right now is consistent with a planet entering a new phase of climate variability, one where natural oscillations like El Nino are amplified by a thermal baseline that has no historical precedent, where the consequences of that amplification extend from storm corridors in the Midwest to grain markets in Southeast Asia, and where the distance between a weather event and a global disruption is shorter, and growing shorter still than most people realise. The storms will pass, the damage will be assessed, the news cycle will move on, as it always does. But the pattern will not pass. The oceanic conditions that are forcing this atmospheric response will continue to evolve. The baseline that is amplifying every signal in the system will not retreat, and the consequences, economic, agricultural, humanitarian, will arrive on their own timeline, 3 to 6 months behind the weather that produced them, quiet and direct and largely disconnected in the public mind from the storms that set them in motion. The question is no longer whether El Nino arrives, it is already arriving. The question is what kind of world it arrives into. What kind of atmospheric behaviour emerges when a natural oscillation of historic potential meets a planet already operating at a new thermal baseline, with no precedent in the records we use to understand normal. The atmosphere over Kansas this weekend is giving us its first answer. Pay attention.